Hey everybody, this is lesson 12.2. It's about areas of parallelograms and triangles. And let's talk about the fact that the area formula for a parallelogram looks like this. Area equals, if I can get my pen to turn on, first thing in this video, having troubles with my pen. The area is equal to base times height. Now, we talked about that formula last time in rectangles. I made a distinction between base and height and length and width. If you don't understand that distinction when it comes to rectangles, you're going to be okay. But if you don't understand the distinction between base and height and length and width in parallelograms, you're going to be in trouble. Okay? So let's talk about that. If you think of base and height just as the same as length and width, here are the measures of these two sides of this parallelogram, 6 and 10. You're going to think that you can just say that the area of this parallelogram is 6 times 10. The width looks to be 10. The other length seems to be 6. 6 times 10 is equal to 60. You'd be way off in this parallelogram. And let's see just how off we are before my showing you the distinction between length and height and base and width. Let's just verify that 60 is not even close to the correct answer. Remember, area is measured in square units. Or another way to think of that is how many squares are there inside that figure? Squares that are 1 unit by 1 unit in each direction. Okay, that would be 1 square unit right there. How many of those square units are in this parallelogram? Well, let's first count the whole squares that we can recognize easily. Here's 1, 2, 3, 4, 5, 1, 2, 3, 4. Right there, all of those, that's 5 wide by 4 down. So there's 20. Okay, there's 20 squares right there. Let me erase that scribble. 20. Here's another 1, 2, 3, 4, 5, 6. Here, let me erase those and let's put some numbers in. There's 3 there. There's 2 there. There's 1 there. Here's another 3 whole squares, 2 whole squares, 1 whole square. That looks like that's pretty close to 1 whole square there. That's really close to 1, just a little bit less. What else? Well, let's see. These 2 here make up about another 1. So how many do we have so far? 20, 21, 22, 23, 4, 25, 6, 7, 28, 31, 2, 3, 34, and a couple of broken pieces. I would say like 37, 8, 9 at most by the time we add up those little broken pieces, like not even 40. And we've calculated 60, right? So there seems to be something very much wrong with using the 6 and the 10 as the base and the height in this formula. But the formula is base times height, okay? And the 10 can be the base, right? Base can be any side of the parallelogram that you want. Excuse me, I gotta get my eraser. Base can be either side, so I'm going to use the 10 as the base. But then the height, I was saying this last time, base and height must be lines that are at right angles to each other. Whatever direction they're going doesn't matter. They can be at any sort of angles, okay, with respect to the page, but they must be at right angles to each other. So if I'm going to choose this 10 to be the base, then the height of this parallelogram must be a segment which is at a right angle to that base, and also it extends as far as the opposite side, exactly that far and no farther. And since this is a parallelogram, it would be at a right angle to that opposite side as well. That would be the height. Now notice that height could have been drawn drawn here, 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 okay? All of those are the same length. They're all perpendicular to that base. For that matter, it could have been drawn from here down to the extension of that side, or it could be drawn from here up to the extension of that parallel side. Those are all good places to draw the height. But now let's just look at one of those locations and see how long that height is. Right? From here to there, that's 1, 2, 3, 4. That's the height. And so the area of this parallelogram is not 6 times 10, but rather the base 10 times the height 4 is equal to 40 square units. And we were coming pretty close to 40 as we were counting up those squares, right? I mean, when I was counting them, I was saying, looks like 37, 8 at the most. But I was really just kind of guessing there. I mean, it was getting close to 40. This formula tells us it is exactly 40, and I think I can convince you that it really should be exactly 40 by doing this. This is what you can always do with a parallelogram. Let's chop off that triangle over there, and let's just slide that triangle. Let's imagine snipping it off with scissors and sliding it over to the right side of that parallelogram. So we've got a triangle. Let's see, 1, 2, 3, 4, a little bit more than 4 units over there, 4 and a little bit, looks like about 4.5 units wide, and it's 4 units tall. So we've got to go 1, 2, 3, 4.5 units wide, and then, oh, look at that. It reaches right to that other corner. So imagine, again, we've taken this triangle and we've literally cut it off with a pair of scissors. It's gone, okay? And we've just relocated it over here. And so now we've taken this parallelogram and we've actually created a rectangle out of it. Now, what's the base and the height of this rectangle? Well, the total base of that rectangle is exactly the same as the base of the parallelogram that we started with, because we took this little piece of the base and we just relocated it over here. So the base of this parallelogram is still 10. And what is the height of this parallelogram? It's 4. Okay? You can do this with any parallelogram. Chop off one end of it as a triangle, reposition it to the other end. You've got a rectangle whose height is the same as the original parallelogram. Okay, so there's kind of another explanation as to why the formula should be what it is when you understand that the base and height are perpendicular to each other. Okay, so there's the formula for parallelogram and for rectangles, of course. Okay, now for triangles, you probably remember that the formula for a triangle is 1/2 times base times height. Or it could be written as base times height over 2 algebraically. Those are exactly the same thing. Why is a triangle formula that way? Well, again, base and height must be at right angles to each other. Okay, so if we're going to take this 10 to be the base, then the height must be at a right angle to that purple base. Okay, so it can't be either one of the other two sides of this triangle. Neither one of those two sides is at a right angle to that purple base. If you're going to draw a segment which is at a right angle to that base, pick any spot along the base you want and draw a segment that extends upward at a right angle. Now, how far do you go? Do you stop there? Is that the height? No, where you stop is when you get to a point that would be on a parallel line to the base that goes right through the opposite vertex of that triangle. That's how high the height is. Think of this triangle as like a mountain, and we're asking, what is the elevation of this mountain? How would you measure the elevation of this mountain? You certainly wouldn't measure it by extending a tape measure okay, or one of those rolling devices that people use sometimes to measure distances. You wouldn't measure that way. You wouldn't measure that way. You'd get two different measures measuring those two ways, right? The elevation of the mountain is from the top of the mountain straight down, is what people like to say. But what we really mean by straight down is at a right angle to the ground. I mean, this is a straight line. This is also a straight line. So you're not clear when you just say draw it straight. You got to say draw it at a right angle to the ground, right? Same thing if you're flying in an airplane. Okay, if here's the ground and you're in an airplane up here and you want to know what's the altitude of the airplane, you don't measure the altitude from the plane this way, right? When I ask students, I say, where should I draw that line? And they go, draw it straight. And I say, I did draw it straight. That's a straight line. Right? Trying to get them to be more precise with their language and say, you've got to draw that altitude at a right angle to the ground. See, there's a triangle here, but the altitude or the height is from that point of the triangle at a right angle to the ground. Okay. So that's the height of that triangle. Now, where's the 1/2 come from? Why is 1/2 part of the formula? Well, because for any triangle, absolutely any triangle, you could create a congruent copy of that triangle, flip it around, rotate it 180 degrees, put it side by side with the original triangle, and look, you've got a parallelogram. Okay. What would the area of this parallelogram be? The area of the parallelogram would be this base 10 times this height 4, but the triangle is only half of that parallelogram because there's two triangles in that parallelogram. So the area of the triangle would have to be 1/2 times 10 times 4. Okay, so there's an explanation as to why 1/2 needs to be part of that formula. Let me give you another illustration of that. Think about rectangles again. Let me just draw one real quickly over here. We know that the area of this rectangle would be base times height. Well, cut that rectangle into two triangles. Right? Each one of those two triangles is going to be exactly half the area of that parallelogram. And so the area of a triangle is going to be 1/2 times, let's say this is the base. And this rectangle, of course, has sides that are at right angles to each other. So for this triangle here, we can use two sides of the triangle, the lengths of two sides in our formula, because those two sides are at right angles to each other. In lots of triangles, there are no two sides that are at right angles to each other. Okay. Finally, well, no, I'll save the finally for the actual, for the next page of notes that we're going to do. So we're done here with an explanation of why the formulas are what they are. Now let's go into the notes that you should have printed out. Let's see, here they are. Okay. And here are the formulas at the top of the page. The area of the parallelogram, base times height, area of a triangle, 1/2 times base times height. Okay. So we want to find the areas of these figures here, not by counting the squares, okay, which we could do, but that takes a long time and it's susceptible to a lot of error or imprecision. Okay? But by finding a base and a height and using the formula for the area. So ABCD, that's a parallelogram. Okay. So I got to use this formula, base times height, and I've got to find a base and a height that are at right angles to each other. Okay. Well, not difficult for this parallelogram. If I choose this side to be the base, that would be 1, 2, 3, 4 units wide. Now the height must go from this base at a right angle to that base, and it has to go up not that far. That's not far enough. It must go all the way up to an extension of that opposite side, right? If AD is my base, BC is the opposite side. Okay? So just extend that and draw that height until it meets the extension of that opposite side, which would also be at a right angle, of course, because the opposite sides are parallel to each other. So how tall is that segment right there? Well, it's 1, 2, 3 units tall. So 4 times 3 is equal to 12. Okay? That height, of course, could have been drawn not right there at that spot. It could have been drawn, let's say from this point here on the opposite side, straight down. And by straight, again, I mean perpendicular to the extension of the other side. Okay? Either way, that height is going to be 3 units. 4 times 3 is 12. Okay? Thought I had one other thing. Oh, yeah, I wanted to say that, well, no, I'll save it for the next problem. Let's get my pen back. EFGH, that's a parallelogram. Its formula is base times height. Let's choose a base. Now, I said earlier, and this might have gone right past you, you might not have noticed, you can choose any side of the parallelogram for the base. And that is true for triangles also. We'll get to that in a moment, but you can choose any side of the parallelogram for the base. Now, if I choose this side for the base, and that's legal, okay? A base, by the way, students tend to think of that word base as synonymous with bottom. A base does not necessarily mean bottom in geometry, okay? It doesn't have to be at the bottom. A base does not have to be a horizontal side, okay? So we can choose this side to be the base, but then we would need to find a segment that is at a right angle to this purple side here, okay? And GH is not at a right angle to HF, neither is EF at a right angle. I'd have to start drawing a side like that at a right angle. I'd have to draw it until it meets the opposite side, and then I'd have to find the distances of these two segments here, which is going to require a little more work. I'm probably going to need the Pythagorean theorem. There's a much easier route to finding the area of this parallelogram here, and that would be if we chose this side to be the base. How long is that? 1, 2, 3, 4, 5, 6, 6 units tall. Now we need a segment that it is a right angle to that one. See, and that segment's distance much easier to calculate, 3 units wide. So we've got a base that is 6. We've got a height that is 3. The area of this parallelogram is 18. So the lesson here is choose wisely, okay? Choose your base and height in a way that makes them easy to identify. All right, let's go on to IJK, which is a triangle. The formula is 1/2 times base times height. Again, base does not have to mean bottom, but if I choose the quote-unquote bottom side of this triangle to be the base, it's going to be very easy to find the height. Here's the overall lesson in these problems. Always choose a base and a height that are horizontal and vertical, literally horizontal and vertical lines, because their lengths will be so much easier to determine in these problems. Okay, because you can just count them by the boxes. So this is 4 units for the base. Now the height would go perpendicularly from that base. Now where do I stop? I don't stop there. Okay, I keep going until I reach the quote-unquote top of the triangle, which is here. And how long is that? That is 3 units tall. Okay. Or again, think of it this way. If we're trying to measure how high, imagine that this is not a mountain, but a cliff. Okay. And there's some, do I have a blue pen here? Can I get blue? Yeah. And there's some water here. And some guy walks to the top of the cliff here and he's going to do some cliff diving. And you ask him, hey, how high is that cliff? How would you measure the height of that cliff above the water? Well, you would measure it, again, students say straight. But what they really mean is at a perpendicular distance to the water, and that's 3 units high. So whether you draw the height there or there or there, it's always going to be 3 units. The area of that triangle would be 1/2 times base of 4 times 3, which is 6 square units. Okay? Now I'd like to take a second and just verify with a little bit of counting that there do in fact seem to be 6 square units or something close to 6 squares inside that triangle, right? So here's 1 whole square right here, okay? Now, that right there is almost a whole square. It's missing a little piece there. Oh, but let's grab that little extra piece right there. And so there's a second whole square, okay? If we put this together with that, that looks like those 2 pieces might make a third whole square. If we put this piece together with, oh, I'm going to say maybe that piece there, that might make a 4th whole square. And if we put this piece together with this piece, that might make a 5th. And then we're down to this piece and this piece making a 6th. Oh, I got a little piece there that I didn't get, but close enough, right? It looks like if we actually tried to piece squares together, we'd get something pretty close to 6. And the formula, of course, tells us it is, in fact, exactly 6. Okay. All right, I don't need to erase all that stuff. MLN, let's find a base and a height. Again, choose a base and a height that are horizontal and vertical, okay? Well, here's the only horizontal or vertical side in this triangle. So let's choose that for the base. And again, base does not have to mean bottom. In this case, it's the top side of the triangle, right? How long is that? 1, 2, 3, 4, 5, 6, 8, 7 units. What's the height? Well, again, it would go from a right angle until it reaches the opposite vertex of that triangle, and that's 3. So area being 1/2 times base times height, you would get 1/2 times 7 times 3. That's 10.5. You could write your answer as a fraction, write it 21/2. I'd be perfectly okay with that. RST, well, RST has a horizontal segment there and a vertical side right there. And that is 1, 2, 3, 4, 5, 6 units wide. Did I count that right? Yes, and 2 units high. 1/2 times base times height is 1/2 times 6 times 2, which is 6. And then OPQ, let's choose this vertical side for the base, because that's easy to count. 1, 2, 3, 4, 5 units long. And this time the height is going to be a horizontal segment, okay? I talked about base does not have to be the bottom side. It doesn't even have to be a horizontal side. The height does not have to be a vertical side. It just has to be perpendicular to the base. So in this case, the height is actually a perfectly horizontal segment, which is 2 units long. So 1/2 times base times height is 1/2 times 5 times 2, which is 5 units long. You got a good couple of handfuls of problems like these to practice on the homework tonight, but there are others. Okay? Others involving 30, 60, 90, and 45, 45, 90 right triangles. Okay. So let's find the area of this triangle. I've given you the lengths of 2 of the sides. Okay, we can choose either one of those 2 sides to be the base, or we could even choose the other side whose length you haven't been given as the base, but then we'd have to find it. Okay, seems like it would be less work if we choose one of the sides that we've been given. But if I choose this 44 to be the base, Okay. Then the other two sides of the triangle can't be the height because they're not at right angles to that side. Okay. Here's what I can do. I can draw a height right here up to that point. Put a right angle in there. I mean, let's just draw a segment that's at a right angle to that 44 and goes right up to that opposite vertex. Now I have created a 30, 60, 90 right triangle. You see that? You're going to have to do this in, I think, as many as 3 homework problems tonight. Okay? And we know one side of that 30, 60, 90, it's 28 units long. And we know that all 30, 60, 90s are similar to this 30, 60, 90. So if I want to find that height, I can do h over 1 equals 28 over 2 and find out that h is equal to 14. Now I have a base and a height for this triangle. 1/2, because that's part of the formula. The base is 44. There it is. And the height that goes along with that base or corresponds to that base is 14. Okay? 1/2 times 44 times 14, what's that? 44 times 7, which is 280, and 28, which is 308 square units. Okay. Do I have another example like this? No, that's the only one. Okay. But let me redraw this triangle here and show you another approach to trying to solve this problem, which would not work very well. Different color here. We had this was 44, we had this was 28, we had a 30-degree angle in there. Suppose we had decided up front we wanted the 28 to be the base. Then we would need a side that is a right angle to that 28, like that. Okay. Here's the thing. This segment right here from point A to point B would not be a good height of this triangle, because the height of the triangle, if we're choosing this to be the base, would have to go as far, it would have to go about this far, because it would have to go as far as a line that's parallel to this one going through that other vertex there. That would be the base from A to point C. You can't stop there at point B. And sometimes this is a temptation for students to do this. Got to get my eraser here to draw a height there, because look, we've got a 30, 60, 90 triangle there, right? 30, 90, 60, we make this 28. Now they're going to use their 30, 60, 90 work to find out how long that segment is, and then they'll do 1/2 times 28 times whatever that segment is, and they'll get the wrong area for the triangle, because that segment, although it is perpendicular to the 28, is not really a height of that triangle. Okay? So make sure that the height of your triangle always extends as far as a line that is parallel to the base and going through the opposite vertex. Okay. Area of this parallelogram. Okay. So we need, again, base times height. That's the formula. But we don't have any two sides that are right angles to each other here. Suppose we choose this side to be the base, 60. Now I've got to find the length of that segment there, which is at a right angle to that base and a right angle to that base. But that's not a great place to draw that segment. The smarter place to draw that segment would be from this point here, because then I've got a 45, 45, 90 right triangle. Okay? And if this side is 40, that side of the parallelogram, then this side is also 40. Okay? And I know that that 45, 45, 90 right triangle is going to be similar to this 45, 45, 90 right triangle. And if I want to find the height of that parallelogram, height over 1 is equal to 40 over radical 2. So the height is just 40 over radical 2. Now that's not considered simplified because we got a radical in the denominator of the fraction. We recall how to handle that. Multiply by radical 2 over radical 2. And we get, when we multiply those fractions straight across, 40 radical 2 over 2. But then that 40 over 2 reduces to 20 radical 2. There's the height of the parallelogram. So the base now is, the area is 60 times 20 radical 2. Reach for your calculator if you need to do the 60 times 20. That comes out to be 1200 radical 2. That's the exact area of that parallelogram. If I'm okay with a decimal, if I say a decimal is okay, punch it in, get a decimal value. Okay. You're going to have to do this on, I think, as many as 3 homework problems tonight. And then you're going to have to do this also. Find the area of this equilateral triangle. Okay. I give you one side length. Right? So that 20, that could be the base. Base times height. 1/2 times 20, but then we're going to have to find the height. Right? And again, a good place to draw that height would be from the opposite vertex down at a right angle. Now, here's the great thing about equilateral triangles. Equilateral triangles' angles are all 60 degrees, so that would be 60 there, 60 there. If you create a couple of right angles here, what we've done effectively is created 2 congruent 30, 60, 90s side by side, right? And if they are, in fact, congruent to each other, which they would be, we really actually learned that way back in last semester when we were proving how triangles can be congruent to each other. That means this much of that 20 is going to be 10, and this much of that 20 is going to be 10. It's necessary to know that to find out how long that segment's going to be, because that 10 is part of a 30, 60, 90 right triangle. The 20 is not. The 20 is part of the equilateral triangle. Okay. Well, actually, now that I think about it, isn't that side 20 also? Sure it is, right? And this is what we're looking for. Well, that triangle is going to be similar to 1, 2, radical 3. So if I want to solve for h over radical 3 is equal to, let's do the 10 over 1. Multiply both sides by radical 3. And we get h is equal to 10 radical 3. That's the length of that segment right there. So that goes in for the height. If we want an exact answer, we can put all that in a calculator if you need to. You really shouldn't need to. 1/2 times 20 is 10. 10 times 10 is 100. But do not put the radical 3 in the calculator if we want the exact answer. That's how many square units are in this triangle. And you're going to have to do that a few times also. Okay. This is not a short assignment. Give yourself plenty of time to do it. Check the answers. Maybe check the answers as you go instead of doing the whole thing and then finding out after you've done the whole thing that you've done way too much of it wrong. Okay, that would be my recommendation. Good luck. See you next time.